In this video, we're going to study the F distribution, talk a little bit about what it is and how it works, and then we're going to do a couple of common F distribution tests. First, comparing two variances from samples to see if they're equal, and then we're also going to look at an analysis of variance, where even though it's an analysis of variance, its most common use is actually to see whether the averages of three or more groups are equal. And so first let's look at what the F distribution actually is, because I always want people to understand what the distribution we're using is, and that'll help you understand why we're doing the calculations that we're doing. Now, a F distribution, since it's based on the chi-square, we have to go back to the chi-square distribution first. A chi-square distribution assumes that you have normally distributed variables or standard normal variables, and technically a chi-square distribution is when you sum up several normally distributed variables that have been squared. So when you take things, data, deviations, something you're assuming has a normal distribution, and you're squaring them and adding them up, that gives you a chi-square distribution with n degrees of freedom. And n is normally related to the number of things you're adding up. Now, once you understand that a chi-square distribution is squaring and adding, the F distribution is just made of two chi-squared distributions. So you get an F distribution if you make a ratio of two chi-squared distributions. So the technical definition: if A is something that has a chi-squared distribution with n1 degrees of freedom, and B is something that also has a chi-squared distribution with n2 degrees of freedom, take A divided by its degrees of freedom in the numerator of a fraction, divided by B divided by its degrees of freedom in the denominator of a fraction, and that's where an F distribution comes from. And it has 2 degrees of freedom because the chi-squared on the top has a degrees of freedom, and the chi-square on the bottom has a different degrees of freedom. So an F has 2 different degrees of freedom that you have to use when you're looking up on a table. Now let's look at an F table to see how it works with 2 degrees of freedom. Here's a typical F table. Look at the shape of an F distribution. Just like a chi-square distribution, the F distribution is skewed to the right. And also, like a chi-square distribution, the F value cannot go below 0, because a chi-square is the sum of squared numbers. A chi-square can't go below 0, and F is a ratio of two things that must be positive. So we can never have a negative value for F. So it's bounded by 0 and then skewed right. Another thing to keep in mind that is true about F distributions is that the center of the distribution is going to be somewhere in the neighborhood of the number 1. And we'll see why that makes sense in just a few minutes. Now, when you use an F table, you have to have the 2 degrees of freedom. And tables will have one of the degrees of freedom across the top of the table. So here it is numerator degrees of freedom, first column for 1 numerator degrees of freedom, and so forth all the way to 9. And most tables will go over several pages to go to 10 and 20 and 30 and 40 degrees of freedom in the numerator, and several more pages to cover all the possibilities in the denominator. And this table, for example, lists here's 3 denominator degrees of freedom and 5 numerator degrees of freedom. I've highlighted these 5 numbers here where they intersect. These 5 numbers represent that the F critical that leaves 0.1 in the right tail is 5.31, 0.05 in the right tail, 9, 0.025 in the right tail, 14.88, etc. The smaller the the value in the right tail, the bigger the f value will be. You have to move further out to leave less and less probability in that right tail. Now, most f tables you see only report f values for probabilities in the right tail. However, commonly you'll have f tests that where you need a value in the left tail. Now, there are a couple of ways that you can get around this. One is you can change tests to force them to be on the right tail, or you can do what I do. I don't like to use these tables. So let's show you how you can make your own alternative. Now, you can draw a picture at home where you can just draw a generic looking f distribution like this. I have done something a little bit more interesting here. I went into a mathematics program and I asked it exactly what would an f distribution with 9 numerator and 19 denominator degrees of freedom look like. Now, you don't have to be quite this fancy, but I do want to just show you what this particular one looks like that we'll be using in a couple of minutes. Now, you at home, I encourage you just to draw a generic freehand. Use a pen on a piece of paper. Draw this. The only thing that's really necessary are to realize that number one, 0 is going to be on the left end. And second of all, remember I told you that the number 1 is going to be somewhere near the center. And so draw the number 1 somewhere near the center of your distribution that you're drawing by hand. Now, everything else we're going to look up using Excel. There are some other statistics programs. Most will let you do this, but Excel is easy to find. So let's look up some critical values that we can draw on our graph using Excel. Suppose we're going to do a hypothesis test using alpha equals 0.1. And this is going to be a two-tailed test that we'll do in just a few minutes here. So that means that we want to divide that alpha into two parts and have 0.05 in the right tail and 0.05 in the left-hand tail. How can we find those values if we don't want to use a table or we don't have a table? We can use in Excel a function called FINV. So you can type equals FINV. And Excel helpfully, this is probably too small for you to see at home, says that this returns the inverse of the f probability distribution. Basically, what we're going to do here is put in a probability, say 0.05, and degrees of freedom, 9 numerator, 19 denominator. It's important which order you put these in. You can't just switch them any old way you want. You have to have numerator first, denominator second. This tells us that the f critical leaving 5% in the right tail is about 2.42. So let's go back to our picture here and let's put that in here. So about 2.42 leaves 0.05 in the right tail, and we can draw a little line where about where we think that 2.42 would be. Okay, let's say somewhere right around here. Okay, so let me move that so where that's a little straighter. Okay, it's leaning. We'll leave it there. So about 5% of the area in the right tail over here. Now let's go back to Excel and figure out what that f critical value would be on the left. And to do that, we can use equals FINV. And the way tables and Excel work here for the f is we have to tell it how much area is in the right. So if there's 0.05 on the left, 0.95 on the right, and we have to tell it the degrees of freedom again. 9 numerator, 19 denominator. And that f critical value is 0.34 approximately. So we'll type that over here. Now, what if you didn't know which was which? Well, you can figure that out simply in a couple of ways. First, remember that the number 1 is going to be somewhere close to the middle of this distribution. So one of your critical values should be bigger than 1. The other should be less than 1. And so that's a way to remember what's going on. It's another good reason why to draw pictures of these things, even if they don't look very pretty if you're doing them by hand. So let's draw a line here, somewhere about where we think that 0.34 might be. And again, I'm drawing crooked today, but that's okay. You get an idea of what it is that I'm trying to do. Let me try to straighten up that just a little. It's not going to work. That's fine. So 0.34 critical value on the left leaves alpha 0.05, or half of alpha for a two-tailed test over here, and half of alpha on the right. And again, that number 1 is somewhere in the middle. Let's actually go do a test, and then let's come back and see what happens. So the most common simple f-test that you can do, maybe not the most common, but the simplest f-test, is to compare two sample variances to see if they come from populations that have an equal variance. And so the f statistic in that case is just to divide the sample variance on the top divided by the sample variance on the bottom. Now, why, let's go back and look, why is that the same as this? A over degrees of freedom, B over degrees of freedom. You have to think about how you calculate the sample variance. It's a chi-squared, the sum of xi minus x bar squared, divided by n minus 1 degrees of freedom. And so you have the sum of squared things, which is a chi-squared, divided by n1 degrees of freedom. That's what a sample variance actually is. And so we have one on the top and one on the bottom, with n1 sample size minus 1 degrees of freedom on the top for the top variance, and n2 minus 1 for the bottom variance on the bottom. And so let's actually do one of these. You can see how simply this can be done. For a lot of t-tests where you're trying to see if they come from two populations whose means are equal, a simpler version of a two-sample t-test assumes the two variances are equal. You should actually test this without just assuming that they're equal. Test to see if they're equal. So, as a practical example of testing two sample variances to see if they come from populations with equal variances, suppose we have a sample of boys and girls SAT college entrance exams, and I see I'm getting ready to make a mistake here. 10 boys, not 9 boys, and 20 girls. Now why? Because the graph we just made had 9 numerator and 19 denominator degrees of freedom. N minus 1, not n. And so if we have 10 boys in the numerator, n minus 1 will be 9 degrees of freedom, and 20 girls, 19 in the denominator. So let's assume that in these two samples of 10 boys and 20 girls, that the sample standard deviation of boys' scores is 120, and the sample standard deviation of girls' scores is 100. Our F statistic is simply to take those standard deviations and convert them into variances by squaring them and make a ratio. And so 100 divided, let's put the boys on top. 120, it actually doesn't matter which you do. 120 times 120 on the top to get the variance, and 100 times 100 to get the variance on the bottom equals. So let's pause the video and you calculate this, and I'll do the same. Okay, I get 1.44 is our F statistic that we want to compare to those F criticals to see what we get. And so let's bring up our graph again and see where that falls. Let's see, 1.44 is somewhere toward the middle, close to 1. Now remember, 1 is important because if the null hypothesis is true, the ratio of those two numbers should be equal to 1. And so the fact that our F statistic is closer to 1 than these critical values means that we are not going to reject the null hypothesis in this case with 9 and 19 degrees of freedom with a sample of 10 boys and 20 girls. Now, those standard deviations were kind of far apart, 120 and 100. With a sufficient sample size, we could probably reject the null hypothesis. It seems like the problem we have here is we don't have enough power, because a sample of 10 boys and 20 girls is not a huge amount. Now, if we were to redo this test with larger sample sizes, we might reject. Let's do that quickly to see what happens. So let's assume that we go out and collect more data, and instead of 10 boys and 20 girls, we have 100 boys and 200 girls. This will mean that we have 99 degrees of freedom for boys in the numerator, and 199 degrees of freedom in the denominator. What's going to change here is not the F statistic. Assuming that these larger samples gave us the same sample standard deviations, which may or may not happen. Let's assume that's true for the moment. We collect more data, we get the same kind of results. Standard deviation for boys is 120, the girls is 100. The F statistic will still be 1.44 in that case. What's going to change are the critical values. Let's go back to Excel and find what those critical values would be. So we're going to do F inverse, and we're still going to do 0.05 and 99 numerator and 199 denominator degrees of freedom. Much different critical value there, 1.32, and in the denominator, our left-hand critical value is going to be equals FINV, 0.95 in the right tail, 99 and 199 in the denominator. So here we get 0.744 as our critical value. So let's go to our graph and change those. So now with our critical values changed, let's see, to 0.74 instead of 0.34, and over here to 1.32 instead of 2.42. We have to ignore this x-axis here because that's going to be wrong, but you can just draw a different picture freehand at home. Now, where is our 1.44 statistic? Well, it's going to be further away from the number 1 than our critical value of 1.32. And so now, with the same kind of evidence, but with more observations, the same sample standard deviations, but more observations, we can now reject this null hypothesis that the variances of girls and boys scores are equal, since our 1.44 is outside of this middle region. So now let's look at a hypothesis with doing what's called an analysis of variance, which is another very common use of the F distribution. Even though it's called an analysis of variance, it's actually used to look at 3 or more groups and to see if their averages are equal. It's similar to a 2-sample t-test, testing to see if 2 sample means come from populations with equal population means, except here we have 3 or 4 or 5 or 10 groups, and we want to test the hypothesis that the population means of all of these groups are equal. An analysis of variance is kind of a name that makes you think that we're analyzing variances, and in a way we are. Let me tell you before we get started also that there are more complicated versions of analysis of variance. All we're going to do here is the most simple version that sometimes people will call a one-way analysis of variance. Again, the null hypothesis here is we have 3 groups. These are groups of hot dogs. We have three different types of hot dogs. On the left, this is a little dot plot of the number of calories in a sample of 20 hot dogs. Now, these hot dogs are similar in that these are all hot dogs made of beef. These are all beef hot dogs. In the middle group, we have a second group where these hot dogs are made of meat. Not just one meat, not just beef, not just chicken, not just pork. It's a mixture of different kinds of meat. And so these are all beef on the left. In the middle, meat hot dogs. And on the right, these are poultry hot dogs. They are made out of all chicken or turkey or something like this. So our null hypothesis is asking the question, given this sample of data from beef and this sample from meat and this sample from poultry hot dogs, our null hypothesis is that the means of all three groups equal the same thing. So population mean of this group equals population mean of this group equals population mean of this group. The alternate hypothesis says that at least one of these groups are different. So it could be that all three are different from each other, or looking at this graph, what might be more likely is that the population mean of the beef and the meat hot dogs might be the same, but the poultry hot dogs might be different. But again, the alternate, be careful with this. The alternate hypothesis is that at least one is different from the others. So one or more might be different. And in this case, it might just be one that's different, but two are equal. So null hypothesis that they're all equal. So I've already put some data on a graph here, and just to look at what's going on, and if one of them is not equal, I would say maybe it's going to be the poultry here. But how does an analysis of variance actually work? What we're going to be doing, the overall idea is we calculate the sample average for the beef hot dogs, which is this red line, the sample average for the meat hot dogs, which is this red line, and the sample average for the poultry hot dogs, which is represented by this red line. And I have these numbers actually at the bottom of the table here, 156.85, 158.7, and 118.76 for the poultry dogs. And what an analysis of variance is doing is comparing how far is the spread, how far are the calories spread for the beef hot dogs. So we calculate spread by calculating a variance. So we calculate and compare the spread of the calories of the beef hot dogs to how spread out are these averages from the overall average, what sometimes people call a grand mean or an overall average. So we look at how far are the beef spread from their mean, and how far are the meat spread from their mean, and how far are the poultry spread from their mean. So this is where the name analysis of variance comes in. And then we compare those spreads to how far is this mean spread from the overall average, and this mean spread from the overall average, and this mean of the poultry spread from the overall average. We're basically asking, is the within group spread, say within beef, how does that compare to the between group spread, between beef and between meat and poultry? So the kind of language you hear used when you're doing an analysis of variance is you have within differences, within spread, and between spread, between differences. All right? So now let's actually look at some formulas to do this. I'm not as interested in just focusing on the formulas. as some people would. I want you to understand the overall idea, but we'll go through and we'll calculate this formula quickly and do a test. All right, if you keep in mind that any f statistic has to have this kind of form, where a is a chi-squared, it's the sum of squared. I apologize. Somebody just knocked on my door, so I lost my train of thought. So anyway, and f is the sum of squared numbers on the top divided by its degrees of freedom, and the same thing on the bottom. The sum of squared, it's a chi-squared divided by its degrees of freedom. And so the f for an analysis of variance is going to have this structure. It's what we call the sum, SSB, sum of squares between groups on the top, divided by how many groups do you have minus 1. And then on the bottom we have sum of squared within. So this is the sum of squared differences within each group divided by overall sample size minus number of groups minus 1. So what do these things mean, sum of squares between and sum of squares within? The sum of squares between is asking, like in this picture, between groups we're looking at the difference between the red lines and the overall average. Because if they all have the same average, the hot dog mean of all groups should be somewhere around 145.44, right? So we're seeing how far is each group away from the overall mean. Now a simple way to do this, since the overall mean is 145.44, is to just say, well, here we have 20 hot dogs, and the difference between the group and the overall mean here is 156.85 minus 145.44, just this distance. But there are 20 data points. So we need to calculate this difference, this mean minus the overall mean, and multiply it by 20, since there are 20 here. Same thing here. This mean minus the overall mean, but we multiply it by 17, since there are 17 items in that group. And similarly over here for the poultry hot dogs, we have 17 of them, but it's how far is this mean from this mean, multiply it by 17. That is how you calculate the sum of squares between groups. When you see it in a picture, it's not so complicated anymore. Now, I've already done this over in a spreadsheet since I didn't have to do all these calculations by hand. So let me show you what I got, and I'll explain what these things are. I mean, you can do this by hand pretty easily. So this is just the difference between the average calories in beef hot dogs minus the overall, 11.4. And then I squared it. And then I multiplied it by 17. Right? And this is the meat hot dogs. The between the average of the meat minus the overall average, squared, multiplied by 17. Sorry, this top one was multiplied by 20, multiplied by 17, because it's the sum of squares between. So we took the squared difference, and by multiplying by how many there are, it's like we're summing them up, right? And same thing for the difference between the poultry and the average. Since they're less, that's a negative number. You square it, it's positive again. Multiply it by 17 observations, and then we add all those up. That's just the sum of squares between groups. That goes on the top of our F formula divided by 3 groups minus 1, divided by 2. Now the sum of squares within, we're going to do in a similar kind of way. Little bit more complicated though. It can be, but let's go back and look at our graph. We want to take every blue point, every data point, and see how far that point is from its own average within the group, right? Sum of squares within the group. So this blue point minus the red, this blue point minus the red, etc. And do that for every point. And of course, since it's called the sum of squares within, we want the distance squared plus the distance here squared plus that squared plus that squared, and then we go to the next group. This squared, that squared, that squared, and we keep doing that. Now, a shortcut to having to do that for all the points is to use the standard deviation. Now let's see how that would work. So remember, what we want is the sum of squared differences for this sum of squared within, sum of squares within. We want the sum of the differences between each point and its own mean. That's very similar to how you calculate a sample variance, right? I had already calculated the standard deviation of each of these three groups of hot dogs. And by having the standard deviation, if we square those, we get the sample variance. Let me go ahead and do that here. What are these sample variances? Well, these sample variances are the sum of the deviations between each number and its own within group mean squared. And so in order to get the sum of squares within for each of the three groups, we need to undo the bottom part of the variance calculation. We need to undivide or multiply by n minus 1. So we have the variance. To get the top part, the sum of squares within, we need to multiply by n minus 1. So I'm going to just do that here for you. Take the variance, divide it by its degrees of freedom, or n minus 1. Right, so, times n minus 1 here. And now we have the sum of squares within for each of the three groups. Now we need to just add those together. And we have the total of the sum of squares within for this problem. So 28,066.1. So we calculated the sum of squares between that goes on the numerator of this f statistic calculation, and we calculated the sum of squares within that goes on the bottom. Now we need to do one more step, and then we can calculate our f. We have to divide the sum of squares between by k minus 1, the groups minus 1. So we need to divide that by 2. And then we also need to divide the sum of squares within by n minus k minus 1. Now n here is the total n for all three groups added together. So we have 20 plus 17 is 37, plus another 17 is 54. So we're going to divide this number by 54 minus k, which is three groups, minus 1. And on the top, we need to divide by k minus 1, which is 2. So we're going to divide this number by 2. And then we can calculate our f statistic. And while I was calculating this, I actually caught a mistake, which I hate, but here we go. I was thinking about something from doing regressions, n minus k minus 1. It's actually n minus k degrees of freedom there. So with n minus k degrees of freedom on the denominator, I divided by 54 minus 3, so that degrees of freedom here should be 51 instead of 50. And if we do this, on the top of our calculation we get about 8,846, and on the bottom about 550. For an f statistic, now you know why we use computers to do this, an f statistic of 16.07. Now we have to look up an f critical for this test. Now this test is always going to be a one-tailed test, because you only reject the null hypothesis here if the sum of squares between groups, meaning there's a big difference between groups, is large, right? And so you get a large f statistic when there's a large amount of variation between the groups, bigger than the amount of variation within the groups. And so this 16.07, when we go to the table or Excel, we're going to put all of our alpha in one tail. So let's go to Excel and look up this f critical. So this f critical, let's suppose we use an alpha of 0.05. We're going to put the whole alpha in one tail here. And before we go, we need to make a note of these degrees of freedom. So it's going to be 2 in the numerator and 51 in the denominator, because those are the numbers that we divided the numerator and the denominator by to get our statistic here. Now if we go over to Excel, we'll use this same command that we used before, F inverse, so equals FINV, and we're going to put all of our alpha in the one tail, so 0.05 in the right tail with 2 numerator and 51 denominator degrees of freedom, tells us that our F critical is about 3.18 here. Now, thinking back to the pictures that we looked at of F distributions earlier, that 3.17 F critical is going to be closer to the number 1. And again, the null hypothesis in these tests, if the null hypothesis is true, we would expect that the F value should be somewhere close to the number 1. That number 1's kind of in the center almost. And so our critical value of 3.17 is to the right of the center, 1, with only 5% in that right tail. And our F statistic is much further out in the tail than that 3.17 significant or critical value here is what most people would call that. So since the F statistic is bigger than the F critical, we would reject this and conclude that indeed, based on this sample of 54 hot dogs put in 3 different groups, that at least one of these groups is not like the others.